Let's consider some more derivatives involving natural log. Here we have y equals the natural log of x squared plus 2x minus 3. One way to do this would be to just begin applying the natural log rule. So this would be 1 over x squared plus 2x minus 3 to the 1/2. And then I'm going to have to apply the chain rule. So this will be times 1/2 times x squared plus 2x minus 3 to the negative 1/2. And then I'll need to apply the chain rule one more time to get 2x plus 2. Then I can spend a bunch of time cleaning this up. I know that 1/2 times 2x plus 2 would just be x plus 1. So this would become, in the numerator, x plus 1 over x squared plus 2x minus 3. That's not too bad, and it's not awful, but another option on this exact same problem would be to just apply a rule from the beginning, that since the exponent on the base is 1/2, I can just bring that out front and have 1/2 times the natural log of x squared plus 2x plus 3. And what's nice about that is not that the other way was particularly hard, but we're just having to keep track of less things in this case. Right? There's less chance of us making a small mistake along the way. Because now when we apply the chain rule, we still end up with the exact same answer, but there was less chance that we were going to make a small mistake along the way, just by applying a simple property of logarithms. Let's look at another problem. Y equals the natural log of x squared over 3x minus 2. Now again, this wouldn't be a big deal to do it and apply the chain rule a lot, but recall that a property of logarithms is that this can be rewritten as the difference of the two quotients, of the two arguments. So the natural log of x squared minus the natural log of 3x minus 2. And by taking the derivative of each individual piece, again, it just simplifies the things we need to keep track of. This would be 1 over x squared times 2x minus 1 over 3x minus 2 times 3. And cleaning this up just a hair would be 2 over x minus 3 over 3x minus 2. Again, we could have done this other ways, but applying the logarithm rules and just being familiar with them can free us up a bit and save us from some minor mistakes. Let's consider y equals the natural log of x times the square root of 3x minus 1. Now what I see here are a bunch of logarithm properties that we can apply. This is the same thing as the natural log of x plus 1/2 times the natural log of 3x minus 1. And if you're wondering where the 1/2 came from, remember that 3x minus 1 to the 1/2 power allows me to drop that exponent. Now when I go ahead and take the derivative, I'll have 1 over x plus 1/2 times 1 over 3x minus 1 times 3. And knowing some of you, you'll start seeing, oops, this should be x, you'll start seeing a lot of the relationships quickly. And so this will be 3 over 6x minus 2 as a way to clean that up if I wanted to. Let's consider y equals the natural log of the square root of this quotient, so x squared plus 1 over x squared minus 1. Again, since it's that whole thing to the 1/2 power, I can bring the 1/2 out front and then rewrite this as the difference of the two parts of the argument. And again, just by cleaning this up, I'm potentially just saving myself a lot of things that I don't need to keep track of. The derivative then ends up being 1/2 times 1 over x squared plus 1 times 2x minus 1/2 times 1 over x squared minus 1 times 2x. Again, I'm still have to be very fluent with the chain rule. I end up with x over x squared plus 1 minus x over x squared minus 1. Let's get a new screen. All right, this here is a frightening looking function to take the derivative of if you don't know natural log rules, because it's the natural log of x times the quantity x squared plus 3 cubed, all divided by the cube root of 2x squared plus 4. But if you know your natural log properties, then this simply becomes the natural log of x plus 3 times the natural log of x squared plus 3 minus 1/3 times the natural log of 2x squared plus 4, which can be daunting still, but it's significantly easier just because we have a smaller variety of pieces to deal with. The derivative becomes 1 over x plus, what will this be, 3 over x squared plus 3 times 2x by the chain rule minus, let's see, I'll have 1/3 times 1 over 2x squared plus 4, and by the chain rule times 4x. And by the time I just clean this up, it's become something that's not that big a deal, and I'm getting so much better at them because I'm getting familiar with the derivative rule, and I'm becoming fluent with the rules regarding logarithms in general. Let's consider one more. In this case, we've got x squared minus 3 times the natural log of y plus y squared equals 25, and the directions are find dy dx. This is just shades of implicit differentiation. So we've got 2x minus 3 over y times dy dx plus 2y dy dx equals 0. Solving for dy dx, I'll have dy dx times negative 3 over y plus 2y equals negative 2x. And when I divide to solve for dy dx, we would have 2x over 3 over y minus 2y. It's divided the negative 1 out. Here we're asked to find relative extrema of y equals the natural log of x squared plus 4x plus 6. So that signals me to take the derivative. This would be 1 over x squared plus 4x plus 6 times 2x plus 4. I'm going to simplify. Well, I can't really factor, so I'm just going to leave this as 2x plus 4 over x squared plus 4x plus 6. My critical points will be when the numerator equals 0, which is when x equals negative 2, and if the denominator ever equals 0. And let's see, it's not going to factor into anything nice, so I'm forced into using the Pythagorean Theorem. Negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm just going to get some imaginary numbers, so this I don't even have to worry about. So my only critical point then is x equals negative 2. And if I do some sign analysis here, I'll plug in 0, and when I plug in 0 I get 2/3, which is positive. and I'll plug in -3. And when I plug in -3, my numerator is negative, and my denominator would be 9 minus 12 plus 6, which is positive. So I'll have a negative number, which means at -2, I will have a local minimum because the derivative changes from negative to positive. And since it's asking me to actually find the extrema, I'll substitute that back in to the original problem. What I want to know is what's the natural log of, let's see, that'll be 4 minus 8 plus 6, and 4 minus 8 plus 6 is 2, so my local min is -2, the natural log of 2, and that's the exact answer. In our second to last example problem, we'd like to find the equation of the tangent line to 4x squared minus the natural log of x at 1, 4. So I just need this. I need the slope at 1, 4. So y prime would be 8x minus 1 over x, and so y prime at 1 would be 8 minus 1, or simply 7. So the tangent line would be y minus 4 equals 7 times x minus 1. The final problem in our examples here is really just a trick that isn't included but can be helpful with hard derivatives. And so let's consider y equals 2x minus 1 cubed over the square root of x squared plus x plus 1. There's no obvious way to deal with this. U substitution won't help us because the derivative of x squared plus x plus 1 is 2x plus 1. So at least the techniques that we have aren't going to help. But if we were to take the natural log of both sides of this, then we know that the natural log of y would have to equal the natural log of our expression. So this doesn't seem to help because in a lot of cases, natural log in our past we thought made things more complicated. But what's nice about this is we can rewrite this as the natural log of y equals, this will be what, 3 times the natural log of 2x minus 1 minus 1/2 times the natural log of x squared plus x plus 1. Right? I'm just simplifying this by applying a few different logarithm properties. And now what happens if I take the derivative of both sides is I end up with, by implicit differentiation, I end up with 1 over y times dy dx equals, the derivative of the natural log of 2x minus y would be 1 over 2x minus 1 times 2 by the chain rule, minus, this will be 1/2, and the derivative of natural log of x squared plus x plus 1 is 1 over x squared plus x plus 1 by the chain rule times 2x plus 1. And that's what 1 over y times dy dx is. So if I multiply both sides by y, dy dx would equal 6 over 2x minus 1 minus 2x plus 1 over 2x squared plus x plus 1. And remember, all that I did was multiply both sides by y. But I know what y equals because I'm told what y equals from the beginning of the problem. So since that's what y equals, and that's what I multiplied both sides by, I can make the substitution for y. So this is going to be times 2x minus 1 cubed over x squared plus x plus 1 to the 1/2. So by using this technique of taking the natural log of both sides and taking the derivative, I was able to come up with something that I don't think I could have come up with any other way.